Go ahead.
Hello, everyone. Today I'm going to tell you about dataset-learning duality and emergent criticality in neural networks. So I'm going to introduce you Vitalis and my paper. And let's start with the explanation of the title. And also I would like to tell you how this paper was organized. Okay, we consider the mapping from the space of non-trainable variables of neural network to the space of fluctuation of trainable parameters. And we called this mapping dataset learning duality. It's important to emphasize that we consider our network in the state of local equilibrium, and in the state, all trainable parameters and its average value are almost constant and just fluctuate around these constant values. And in this specific case, we can perform linear transformation of variables to obtain a simple enough mapping from one mentioned space to another. And also, we can even reduce the multidimensional task to a set of one-dimensional problems. Then, on the next part of the paper, we investigate the emergence of criticality. More precisely, we are interested in the finding the all possible compositions of loss and activation functions, which leads us to the power law distribution of trainable variables fluctuations. This phenomena can be interesting because this phenomenon prevents neural network from getting stuck in the local minimum because there is no exponential suppression of large-scale fluctuation. Also, this critical phenomena and its description in neural network can be useful in explanation of criticality phenomena in physics. Okay, and let's start with the first part of the paper devoted to the duality, and especially let me give a brief introduction into the frameworks of the fully unconstrained neural networks. Here you can see the neural septuple. Of course, we start with a vector state of neurons, X, and if we act to this vector with the projection operator, we obtain the boundary subspace of neurons. And here you can see the function of distribution of this boundary neurons, which describes a training data set. Also, all neurons in the neural network are connected with each other, and the W matrix describes it. Also, we have B vector, bias vector for every neuron in the system. We can note that the total number of trainable parameters are equal to n squared plus n, but in specific architectures, some trainable parameters can be fixed, some can be shared, and then we can obtain less real number of trainable parameters. And we will denote these trainable parameters as a Q, and we will assume that the measurement of the space is equal to K, which can be less than n squared plus n. Also, we can see here two types of functions. The first one is an activation map, which describes nonlinear part of dynamics of non-trainable variables. And also there is another one function H, it is a loss function, and neural network tries to minimize this function. And this function determines the behavior of trainable parameters, Q. And here you can see the gradient descent equation. So we can see how Q dot can be expressed through the loss function. And this loss function determines the dependency of Q dot on some variables. And we can assume that Q dot is a function of boundary neurons. It's elements of dataset. Also, it is a function of some bulk neurons after the activation dynamics. And also, Q dot can be a function of trainable parameters, but because we consider the neural network in the learning equilibrium, we can consider Q as a set of fixed parameters, constant parameters.
Pardon me, Katja.
Yes.
Dan Humfeld here. One part of the construction that hasn't been clear to me yet, and I'm sorry, this is the first time I've had to actually ask someone about it, is point number 2, this projection onto the boundary neurons. So we might consider the inputs. What wasn't clear about that is essentially what is the form of P. I see we have the trace of P over on the right, which suggests that it is a defined as a matrix.
Yes, it's matrix, and it is a matrix where there are some ones, ND number of ones on the diagonal, and this is a projection. This matrix performs a projection of the X neuron to its boundary subspace. It is a subspace, boundary subspace of the space of neurons space.
No, I think Dan was asking like what the form of this matrix, and you were absolutely right. Said that there's ND1s on the diagonal, all other diagonal elements are 0, and everything else is 0. So it's like identity matrix, but with a bunch of zeros on the diagonal as well. And what it does, as you said correctly, just sets the 0 all of the components of X that are not input, or out.
Great, that is clear. Thank you both for the explanation.
Sure.
Yeah, thanks. Okay, so we can say that Q dot depends on boundary neurons and bulk neurons at the some time when the activation is finished. Also, Q vector is a vector of parameters. Then we can consider this set of equation which describes the activation dynamics, and we can easily see that the value of X bulk vector in the every next time moment is fully determined by the previous values of this vector at the previous time moment. And then combining it all together, we can conclude that the values of bulk neurons after activation is finished can be expressed through the initialization of the neuron vector, and also vector Q is just a vector of parameters. And then we can combine together activation and learning dynamics. We can express this vector state after activation dynamics through the vector state before activation dynamics. And then we can obtain mapping from the space of neurons to the space of fluctuations of trainable variables. And here, for example, you can see this form of this mapping, and this term corresponds to explicit dependency of the loss function on Q, and this term corresponds to implicit dependency of H on Q. And okay, now it's time to turn to the language of probabilities. And here you can see the expression which describes how the probability distribution on the neurons determines the probability distribution on jumps of variable Q. Then we can make some assumption that, that in the initial time when every new element of dataset puts into the boundary, we can put all bulk neurons in this first time is equal to the same values. So we just assume that bulk neurons can be fixed to some variables every time we put new variables to the boundary. And then we can slightly simplify this expression to this one. And here we can see the mapping from the n-partial space of boundary neurons to the k-dimensional space of trainable variables fluctuations.
So the statement is it's a one-to-one mapping. So you reset your boundary condition, reset your data set, input-output data, and then by that you specify the neural network gets to some state, fixed state, where their bulk neurons, the hidden neurons, are also fixed, and that's the statement here, right? So they are not independent random variables, the bulk and boundary.
Bulk and boundary neurons are not independent. And fluctuations of trainable variables are fully determined by the boundary neurons.
Sure.
And on this step, the number of trainable variables is equal to k, and number of non-trainable variables is equal to n partial. Yes, and then we can make some transformation of variables. It's just a linear local transformation, and we are interested in the variables, new transformed trainable variables, for which fluctuations will take place only along n partial directions. And doing this transformation of trainable variables, we can obtain this expression. And here you already can see the mapping from n partial to n partial spaces. So maybe it's important mapping. And then we are going to work with another expression for this distribution of jumps. Here you can see that distribution of jumps can be expressed through this Jacobian in some variables. And we are interested to obtain these elements of the Jacobian in the new rotated variables.
So, Katya, so 314 is your duality, right? So 314 expresses how the distribution of data set variables xd are mapped to the distribution of the fluctuations q dot.
And here q dot is a function, and this q dot is a variable.
So xd are non-trainable variables, and q is the trainable variable. So this is your data set learning duality. Okay, great.
Yes, and then we want to investigate these Jacobian metrics, and then we can rewrite the stochastic gradient descent equation in rotated variables q. And then we can just take partial derivatives and obtain expressions for the elements of the Jacobian matrix. Then we are interested in its diagonalization because we want to reduce our task to the set of one-dimensional ones. And we can just use a singular value decomposition and perform one another rotation of variables. In this step, we would like to rotate both trainable and non-trainable parameters using orthogonal matrices of left and right singular vectors. And in these new trainable and non-trainable variables, we will have a diagonal Jacobian. And it allows us to write the set of such mapping. And here, the one boundary neuron solely determines the distribution of fluctuations of trainable parameter Q.
But it's not one boundary neuron. It's a linear combination of boundary neurons.
Yes.
That determines a linear combination of the trainable parameters.
Exactly.
But yeah, the idea is clear.
It's new variable corresponding to non-trainable variables. Yes.
Sure.
And so this is a result of this part, because now we know how to consider neural network in the state of local equilibrium, and we know how to describe distribution of jumps in this simple manner when we perform the reduction of the task. And now I'm going to tell you about our toy model, on the basis of which we then going to investigate the critical phenomena. So what is a toy model? We have just two neurons, XY, it is an input neuron, and X2, which is an output neuron. And these neurons are connected with a trainable weight W and bias B. And also, we have only two possible values for X2 neuron, and we are going to consider two different cases for one value of X2 and for another value of X2. And for these two cases, we can write down the...
So it's like classification task. You have some data on X1, and then you want to classify it to sets.
Yes, for example, we can solve the problem of classification of images of zeros and one from the MNIST data set. And we just use the more informative pixel from the data set as an input value. And then we will obtain exactly this task. Okay. Here, for this simple toy model, we can perform not local transformation of variables. And for two different values of output neuron, we will obtain these two forms of trainable variable fluctuation. And it is a function of input neuron. Okay, what we are going to do further? We can we can write down this expression for the distribution of few gems. And here we can see that there is no Jacobian, but in this model is just derivative. We can write it, we can calculate it, and then what we would like to consider. We are going to require the function of distribution of jumps is equal to some power law function. And we can assume, we can make assumption in this step that this power law came from this derivative, not from the initial distribution. And then we are going to require that both these derivatives of real trainable variables have power law form. And then our task is to find all possible combinations, all possible compositions of loss and activation functions, which leads us to these power law derivatives.
So
And
another way of saying you don't want the data set to have criticality. You want to see whether the criticality can emerge from learning itself.
exactly, yes.
Okay.
Now we consider some we prepared extensive analysis, but I will just briefly tell you main steps and results. So we start to consider this derivative, W dot as a function of x1 input neuron. We require this function as a power law function. Then we can just solve this differential equation for different values of kw. So you can see it at the bottom. Also, we can use the stochastic gradient descent method. And then we can rewrite this equation in this manner. And y here is a linear combination of weight, bias, and input neuron. So then we are interested to find h loss function as a function of the full argument of activation function. So this function, h as a function of y, is a composition of activation and loss function. And I will name it h, which depends on y. Okay, and then we can put a different solution for W dot on the left side of this equation and consider different differential equation. For example, we can assume that W dot is equal to exponential. We consider this solution. Then we will obtain this expression and we can solve it. And here we can conclude that exactly exponential form of h as a function of y leads us to the power law function for this derivative. Okay. Then we can find other functions which leads us to this power law derivative, W dot with respect to xy. So we can find exponential function, we can find linear function, quadratic function, and logarithmic function. Also, we can note that we are not interested in linear function because it hasn't no local or global minimum. Okay. Then we can make the similar and even more
sorry, Katya?
simple. Yes.
Doesn't that same argument apply to the exponential activation function? It has no local or global minima or maxima.
There is a minima in the infinity, right? So if you have a negative exponent, so there is a plateau.
There is a minimum at infinity and a maximum at
negative infinity.
Of course,
So
and that also applies to the linear case, does it not?
no, a linear case is just on either positive side or negative side, it will go to minus infinity, but exponential can go to zero.
Exponential, yes.
So take exponent
So there
to
is
the
a
minus.
minimum, not a maximum. Okay.
Finite
Clear.
limit.
Thank you.
Yeah. We don't care about maximum. We don't care about maximum loss. We want to find minimum of loss functions.
Okay.
But you are right. Linear function wouldn't work, but exponential is kind of a marginal case because you may have a loss function which is like if you have this runaway, you going to the left in the exponential, then your loss function stops changing. You can never get to the true minimum because it's in infinity, but
you can get arbitrarily close.
Yeah, exactly.
Okay, we can find a suitable function on the comprehending about this derivative, and we can make the same for this derivative. And for both cases, we can conclude that we are interested on only exponential, quadratic, and logarithmic function to consider the power law of the distribution of trainable parameter.
So actually, back to Dan's point, I mean, logarithm also doesn't have a minima, right? But I think the point here was that, you have whatever complicated loss function you have in some regime, in some range, it can be approximated as one of those functions. And if so, like say negative logarithm, yeah, it runs away and eventually it will reach infinity. But then as it does that, what would be the fluctuations of the trainable variables? But strictly speaking, logarithm also wouldn't, even 1 over logarithm. Oh yeah, 1 over logarithm would be fine, but that's not the function you're analyzing. Minus logarithm wouldn't have, or positive.
Will some additional comments when we will consider some specific cases.
Yeah, but that's a good point. That's a good point. Mhm.
Yes.
Right.
And also, okay, we identified these functions, and we also know corresponding to them powers, KW and KB, which are the same for exponential and logarithmic cases and different for quadratic case. Okay, and now let's move to the numerical experiments and numerical results. We can consider values of output neuron is equal to 0 or 1. And we used in our simulation Gaussian distributed input values with a variance 1/4. And then we used different combinations of specific functions, activation and loss function. And here you can see that in some scale limitations, these combinations, specific combinations, lead us to one of these 3 forms of h as a function of y. Let's consider.
I see. So sorry, Katya. So you do have logarithms in 8.6 for any particular x1 input, and there wouldn't be any minima. But since you are looking to combine those two things together, two terms,
Yes.
logarithmic terms, then together they do have a minimum, and that's
Yes.
kind of the point. All right.
Because
Yeah.
what in this example we will have different functions for zeros and ones.
Yeah.
But
if you have linear functions and you combine them, you'll always get a linear function, and that will never have a minima. Okay, that's makes sense.
Now let's consider sigmoid activation and mean square loss function. And then in some regime, activation function is just exponential. When the y is large negative. And then we can consider the case when x2 is equal to 0, and then h as a function of y is exponential. And in this case, we can expect that we will have in this limitation power law distribution of Q fluctuations with a power which is equal -1, because we have a -1 for exponent.
Well,
And
let me back up one more question regarding the combination of those two logs. We see the x2 there. Earlier we talked that x2, earlier you defined that variable x2 as being a dual state variable. It's either 1 or 0. And so
Yeah.
with that restriction of x2 being either 1 or 0, then the cross entropy loss function does not have a minimum or maximum. Is that
Yeah,
correct?
the loss function doesn't, but the average loss function does. Yeah.
Average loss function.
Yeah, so it's like for every even if you only have one classification image, yeah, it will just keep going to one place indefinitely. But then because there are combinations of within your data set, so if you take average x, then it will have a minimum. Yes, Katya, that's.
We will put dataset elements corresponding to zeros, then corresponding to ones. Then after some time, the neural network will come to the state of local equilibrium because we have different functions for h as a function of y for zeros and ones.
Yeah, but
Great,
if you had only zeros in a data set, then there wouldn't be a minimum there. There would be a
No.
runaway. Yeah,
Yes.
that's the point. Yeah.
Because we consider two types of images. Yes.
Yep.
And here is, you can see numerical results. Numerical results corresponds to blue dots. And we can see that in some region of scales, we can see in logarithmic axis, linear function, straight line for distribution of jumps. And its incline is close to -1. So in normal axis, we would have a power law distribution with a power is equal to -1. And we can make the same for ones images, for example. It was for zeros and it's for ones images. Also -1. If we will use a combination of sigmoid activation and cross entropy loss function, we will also come to the exponential form of h function, and we also will expect the -1, and we will have it. Here I would like to say that the blue dots are not really straight line, because at first there is some limitations for scales, and also everywhere there is an effect coming from the initial distribution also. It may be also the reason of deviations from the straight line. Okay.
Do you mean initial distribution, or do you mean distribution of the input
Input
of the data set, not the initial? So you are plotting the combination of both Jacobian and the data set distributions, and you are saying that the power law only comes from the Jacobian, but the other part can kind of change your power law distribution to something else.
Exactly, thank you.
Yeah.
And then we just performed very similar experiments, but for another combinations of loss and activation function, which also lead us to the quadratic composition. Here you can see power is equal to 0 because the contribution from B dominate. And also we consider combination of piecewise linear activation and cross entropy loss function, which lead us to the logarithmic composition with k is equal to -2. And also we have this incline in numerical results. So also there is some interesting part about fractional powers when we don't require strict power law distribution. And making these reasonings, we can come to conclusion that we can consider H with arbitrary even power. So maybe also interesting because it leads us to another powers of the power law distribution, which are fractional. And here you can see also good results and a table which take all results together, and we can see that we have 4 types of H functions, composition functions. On the right side of this table, you can see that there are some examples, specific examples of this function realization. And on the left side, you can see corresponding powers of the power law distribution. And finally, I would like to say that we performed this extension analysis for simple one-dimensional task and toy model. But previously, on the first part of the paper, we reduced our multidimensional problem to the set of one-dimensional ones. So we can assume that we will have similar results for even multidimensional problem because it can be transformed to the set of one-dimensional problems using just linear transformation of variables.
And only in the limit where this perturbative approach works, right? When you are,
yeah.
Because you are doing this local rotation of variables that gives
yes,
you that,
and when we consider a local minimum of the local equilibrium of the neural network, it should work. Yes, I think that's all about our paper. What I wanted to say.
Thank you, Katya. Questions?
Thank you for the presentation. You've answered all of my questions.
Thank you.
Thank you.
Okay, so if no questions, thanks everyone for coming. Thank you, Katya, for a great presentation, and I'll see you guys next week. Thank you. Bye-bye.
Thank you.